Okay, this is going to be the video for chapter 17 for AP Statistics. We're going to do this in two halves, actually, because we usually teach this over 2 days. But chapter 17, which is the last chapter in the probability unit, has to do with two probability models that are standardized. One's called the binomial model, and one's called the geometric model. There are a number of probability models where certain situations come up over and over and over again, so we have a standardized way to handle it. And it could be that we could use the formulas and or combinations and things like that from chapter 14, 15, but there's a faster way to do it because it's already been kind of pre-solved for certain situations. So the binomial is one, geometric is another one. If you've taken brief calc before, we introduced the binomial model as well as another one called the Poisson model. But we're just going to do binomial and geometric here because this is what's included in AP statistics. These are very helpful and they make it much easier and faster to calculate probability in advanced situations than it would be if we used the regular methods. Okay, so we're going to talk about both the models today, geometric or binomial and geometric, and then in the second video we'll talk about some extensions and ideas about how to use those models in different ways. Okay, so first of all, let's take a look at a situation that's pretty complicated, but we have methods to solve right now, but it would be pretty involved. So let's say that at a college, 60% of the students voted in the latest election. If you were to select 3 students at random, what is the probability that exactly 2 of them voted in the election? Okay, so you could list the sample space out with a tree, put the labels of the probabilities, so you have yes for they voted, no that they didn't vote, and the second student could yes or no vote, and then the third student. And the probability of all the yeses is 60%. These are independent, and the probability of that student not voting is the other 40%, right? And so we would have 1, 2, 3, 4, 5, 6, 7, 8 different possible outcomes, like yes, 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 no, yes, and so on, of which ones voted and which didn't. But exactly 3 of those cases would include 2 people voting and only 2. Either the first 2 students voted, or the first and the third 2 students voted, or the second and third students voted. Anything else would involve more or less students voting than 2. And because we multiply across the table, because it's the first student voted and the second student voted and the third student didn't vote, we would multiply this 0.6 times 0.6 times 0.4 to get this outcomes probability. And then there would be a 0.6 times 0.4 times 0.6 for the yes, no, yes case. And there would be a 0.4 times 0.6 times 0.6 for the no, yes, yes case. But because these things were independent, all 3 of these really are the same probability, right? If we then wanted to, the ordering here is just a little different, right? It's 0.6, 0.6, 0.4, 0.6, 0.4, 0.6, and 0.4, 0.6, 0.6, right? But then to combine these cases, because it's either yes, yes, no, or yes, no, yes, or no, yes, yes, or is add, so we would add those probabilities. So the probability that exactly 2 voted is the probability of yes, yes, no, plus the probability of yes, no, yes, plus the probability of no, yes, yes. And that would be the 0.6, 0.6, 0.4 plus these other 2, right? But each one of these terms has 2 0.6s multiplied and 1.4 multiplied. And so there are 3 identical terms. So we could write this as 3 times 0.6 squared times 0.4 to the first power. 2 0.6s, 1.4 multiplied 3 times because we're adding 3 cases, right? And that 3 actually could be thought of as a combination. So we haven't talked a lot about combinations and permutations, but a combination or permutation is when you select some items without replacement out of a group. Combination is when the order doesn't matter. So if I were to say, all right, we've got our 3 students and we know that 2 of them voted, how many different ways could that be, right? So let's see the number of ways that we can choose which 2 of the 3 voted. In other words, we've got, now that we know we're asking 3 students, right? And we know that 2 of those are yeses, how many ways could we place the 2 yeses, right? Well, there are 3 different spots to choose from, and we choose 2 of them. And it doesn't matter if I choose this one and this one, if I choose that one first and then this one, or if I choose this one first and then this one. So the order that I place the yeses doesn't matter. I still get no, yes, yes. That's a combination, choosing 2 spots out of 3 where order doesn't matter. And 3 combination 2 turns out to be that 3, right? So you could think of it this way, that this probability calculation, which we have to do this complicated tree and or rules and everything, could be solved by just saying 3 combination 2 I select 3, 2 of them are voting, so 3 combination 2, and then the probability of yes, which is voting, squared, times the probability of no, not voting, 1 time. Right? So people notice that this kind of situation happened very frequently, and also that this particular structure looks like something else in math. So this is actually called the idea that we have multiple trials of the same thing. The probability is constant of the yes and no cases occurring. There's only 2 possible outcomes, something that we can call success or yes, and something that we can call no or failure. In this case, success or yes would be voting, no would be voting. So if you have a two situation, yes or no, the probability of yes and no is staying constant. You have multiple trials of the exact same thing being done, and they're all independent of each other, where the probabilities don't affect each other. If the first one voted, that has no bearing on whether the second person voted. Then that situation is referred to as a Bernoulli trial. Okay? And then there's 2 different models that can be done based on Bernoulli trials. One is this one, which is called the binomial probability model. Okay? And so what makes this a binomial probability model is that we're running a fixed number of trials. We have 3 students, and we're specifically finding the number that are yeses out of the total, right? So if we're finding the probability of a number of yeses out of a total number, then that, and we have a Bernoulli trial, then that means we can do this whole thing with what's called the binomial probability model, which means instead of doing that whole tree, we can just jump straight to this. We can just say, okay, N is going to be the number of trials, K is going to be the number of successes, P will define as the symbol for the probability of the success or the yes, Q will be just 100% minus P, so the rest of the probability of the no case. We'll have K yes cases and N minus K no cases, okay? So let me show you how we could do that problem over again. If we thought about the problem, what I could do is this. Let's do this on another page. Let's say I was given this problem. I would say, all right, I want to find the probability that 2 out of 3 people voted in a selection. The probability of somebody voting is 60%, okay? So maybe I'd ask myself, wait a second, it seems like the same thing is happening again and again. Is this a Bernoulli trial? Well, to be a Bernoulli trial, we have to have multiple trials of the same thing. Yes, we have that, right? Each student is a trial. In other words, every student that I ask, did you vote, is a separate trial. Is the probability of yes, in this case of voting, 60% constant? Yep, we're making the assumption that each individual student I asked has a 60% chance of voting. Are the trials independent of each other? Yes, we're assuming that this is a random sample, so there's no connection between the students, okay? So we have multiple things, constant probability, independent. This is in fact a Bernoulli trial. And then if we're finding the probability of a number of yeses out of a total, which we are, that makes this a binomial problem. Okay, and so what that means is instead of doing the tree, I can just say, okay, the probability of 2 out of 3 is 3 combination 2. The probability of voting, which is 60%, and 2 people have to vote, and the probability of not voting is 40%, and 1 person has to not vote. And then I could do this in a calculator. So if we were to bring up a calculator here and go 3, and then math, and then over to probability menu where the combinations and permutations are, 3C2, that number would be 3. So it'd be 3 times 0.6 squared times 0.4 to the first. So we would just go 3 times 0.6 times 0.6 times 0.4, and we would get the probability as 0.432, right? That's the same thing we would get if we went to all the trouble of doing the tree and calculating it all out. We're going to get the same thing, but this is a whole lot more work. So we could use our old probability rules, or we could use this nice new model called the binomial probability model to get to the answer super fast, okay? So this is basically an accelerator. It's a way for us to calculate problems much faster if they meet their criteria, all right? In fact, this happens so frequently that the calculator has a function in it that's devoted to it. It's called the binomial PDF function. And it's in the same spot as normal CDF is. Okay, so binomial PDF, let's take a look at where it is. If you go to the distributions menu, so second and variables key, where we find normal CDF, if you keep scrolling down here, there are two functions here named binomial. There's binomial PDF and binomial CDF. So if I select binomial PDF, one of two things is going to happen. If you have a TI-84, it's going to give you a little entry screen that asks you to put trials in. If you have an older TI-84 or a TI-83, it's just going to say binomial PDF with a parentheses, just like normal CDF. You're going to have to remember that the first number you have to enter here is the number of trials. Since we're asking 3 students, we would put a 3 in there. And then the P is the probability of the success case. In this case, it's 0.6. We enter it as a decimal or a fraction. So I'm going to put 0.6 in there, or 6/10. And then for the X value, that's the number I'm interested in. I'm wanting the probability of exactly 2 people voting. So the 2 out of 3 means I'll put a 2 in there, and then I hit paste. And when I run it, it gives me that same 0.432 in literally a single step in the calculator, right? So binomial PDF is doing this calculation behind the scenes, okay? So that's called the binomial probability model. Let's look at a couple of offshoots of that, okay? Slightly different problem. At a college, 60% of students voted in the last election. If you select 3 students at random, what's the probability that up to 2 of them voted in the election? Which means we'll count it as successful if none of them voted in the election, 1 or 2, but not all 3. So of the cases 0, 1, 2, and 3, we want to include 0, 1, and 2. Okay, well, we could use our new model. We could say, all right, there's a 60% chance of voting. So if I ran binomial PDF, 3 cases, 60% chance of 0 of them voting, I could change that last number to 0, and then add, because this is or, we add another case with 1 person voting, or we add another case with 2 voting. You could add those all up and you would get a certain number. In fact, let's do that. So if I went second variables, binomial PDF, okay, out of 3 students, 60% chance of voting, 0, right? That turns out to be, this probability is 0.064. And then if I add to that the same thing, actually I'm going to do this a little faster. I'm going to copy this, paste it down here, and then just go in here and change this to a 1. Has the same effect. That would be 0.288. And then I could add a case for 2 of them voting. So let me go down here and copy that and put a 2 in there. And that would be 0.432. And so then if I added those up, that would give me a total of this number plus this number plus this number, and give me a total probability of 0.784. So there's a 78% chance that up to 2 people voted, okay? But this situation occurs so frequently that we have to add numbers from 0 up to a number 2, that there's another calculator function called binomial CDF, where the C stands for cumulative total from the left up to a value 2. So if you run binomial CDF out of 3 up to and including 2, that's the other function on the calculator, same location. If you scroll down here to binomial and select the C version, right, 3 trials, 60% chance of success, up to and including 2, we're going to get that same 0.784 in just 1 calculator step instead of 3. So the calculator has this special model built in, and you can use it to find the probability of one of the cases happening. Like we could have 0 voted, 1 voted, 2 voted, or all 3. So I could use binomial PDF with 2 to find the probability of just exactly 2 voting. But if I wanted 0, 1, and 2 cumulatively totaled up to including 2, then I switch to the C version of the formula. All right, so that's called the binomial probability model, and our calculator has a particular, I think of the P as the particular value and the C as a cumulative value, although really it stands for probability density function. All right, here's another variation. At a college, 60% voted. We asked 3. What's the probability that at least 2 voted in the election? So what I could do is I could make a random variable here for the number who voted, list out the cases, right? None of them could vote, 1 could vote, 2 could vote, or all 3. Then I could say, wait a second, okay, I want at least 2. So that means this part over here, 2, 3. There's 2 ways I could do this. Because it's 2 or 3, I could do a binomial PDF for 2 and add it to a binomial PDF for 3. But instead, what if I was a little cleverer and said, wait a second, this plus this together has to add up to 1. So to find this probability, I'm just going to take 1 and find this, subtract off this probability. So this probability over here, this probability, is going to be given with binom CDF, cumulative total. 3 people were asking, 60% chance of voting up to and including 1. And that means that this probability over here is just going to be 1 minus that probability. Binomial CDF, 3.61. So what I could do is I could run my binomial CDF function and say, okay, 3.6 up to and including 1, that gives me 0 and 1 case added together, right? That's 0.325 or 352. And that means that the probability I'm after over here would be 1 minus 0.352, right? Which is the other 64.8%. So very flexible model here. All right, Bernoulli Trials binomial model, C for cumulative total. And basically the way I remember it is, if you're trying to find the probability of exactly 1 case, like this, then you use the P version. If you want the cumulative total to the left of a boundary, you use the C version. And if you want the cumulative total on the right side of some boundary, you take 1 minus the cumulative total of the left side of the boundary. Okay. Okay, with this, you should be able to do the first problem in the Chapter 17 required practice packet. So pause the video, give that one a try, and then we'll work through that real quick. Okay, so let me work this, and I'll show you how I would quickly do this with this binomial thing. It says, wildlife biologist examines frogs for a genetic trait he suspects may be linked to sensitivity to industrial toxins in the environment. Previous researchers have established that 1 in every 8 frogs has the trait. He collects and examines a dozen frogs. So the sample size here is 12. And it seems like finding the trait, the probability of finding the trait in a single frog is 1 out of 8, okay? If the frequency of the trait is not changed, then what's the probability he finds the trait in none of the frogs? So let me show you how I would do problem A. Okay, I like to do it this way. I would say, let's have a random variable to be the number of frogs with the trait. And I'll list the possibilities. None of them, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, or 12. This is a listing of the sample space, right? Okay, and then I'm going to say, all right, what's the probability that just one of them? That's one possibility. So the probability that I would have none, the probability that the number of frogs with the trait would be 0, that would be just found from binomial PDF, right? This definitely is a binomial situation. I have multiple trials. The probability of the thing happening is staying constant. It's 1/8 for every frog. The trials seem to be all independent, and I'm finding the probability of a number out of 12. And so we've got binomial PDF here. That means out of 12 trials, the probability of the trait happening is 1/8, and I want the 0 case here because I want just this one case 0. So I would just go straight to the calculator and go binomial PDF. We're looking at 12 frogs. They have a 1 divided by 8 chance of having the trait, and we want the probability of 0 of them having it. And that's 0.2014. Okay, so calculator setup. It's good to write this out. This is a great way to kind of sketch the sample space. Let's do another example. B, the probability of at least 2 frogs. Okay, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. At least 2 is all of this part over here. So what I'm going to say is this is 1 minus this. So the probability of having, I'll use black here, the probability of having x be at least 2, greater than or equal to 2, is going to be 1 minus the probability that x is less than 2, right? 0 and 1. And so that's just going to be 1 minus, and I'll do a binomial CDF function because I'm combining a cumulative total of a bunch of cases here. Binomial CDF out of 12 cases, 1/8 chance, up to and including 1. So you stop at the last case you're including, right? So if I did binomial, I'll scroll up from the bottom. That's a little faster. I want the C version this time. 12 frogs, 1/8 chance of having the trait, up to and including 1. That's point. So this probability over here is 0.5467. So 1 minus 0.5467 gives us the probability on the right-hand side. So 1 minus that, answer is 0.4533. Okay. All right. And then the next one says, what's the probability of having 3 or 4 frogs? Okay, so that means of the possibilities, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and 12. I want just these two cases, 3 and 4. Okay, there's no, I mean, I could be clever and do subtractions and stuff, but I think I'm just going to resort to a binomial PDF for this case plus a binomial PDF for that case. So the probability of x being 3 or 4 frogs would be, I would do a binomial PDF because that applies to a single case for 3 frogs having it. And then because it's or, I would add binomial PDF 12 1/8 for the 4 case, right? So let me just do that all together here on the line here. Binomial PDF, 12 frogs, 1/8 chance, 3. That one is 0.1292 approximately. And then if I just go up and grab that again, but change this to 4, it's 0.0415. So when you add those, if you took this number and added it to this number, you'd get 0.1707. Okay, so you can use P twice, one for each case that's included. Okay, and then the last example there is the probability of no more than 4 frogs. So 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 are the possibilities. No more than 4 means up to and including 4. So I'm going to do that. Probability of no more than 4 frogs is going to be binomial CDF because that's a left-hand case. Binomial CDF out of 12, 1/8 chance of having the trait up to and including 4. All right, so binomial CDF, 12 frogs interviewed here or tested, 1/8 up to and including 4 would be 0.9887. All right. Right, so that's the first good example. And that's a good example of the use of the binomial model. Okay, the next thing we're going to talk about is the other model, which is geometric model. There are formulas in the calculator. They're called geometric PDF, geometric CDF. But there's a little bit difference. This is also that you have a Bernoulli trial, so multiple things happening, same probability of success, independent trials, but there's something different. In this case, instead of talking about the probability of a number out of a number being successful, this is going to be the probability that the first success occurs on a specific trial in the order. Okay, so let me give you an example. At a college, the same setup, 60% of people voted, but instead of interviewing 3 students, we're just going to keep asking students one at a time until we find the first one we find that voted, and then we'll stop. And then we're going to ask, what would be the probability that I have to ask the third student? It would take the third student would be the first one that told me yes, they voted. So the tree would look different if I tried to do this with a tree, right? The first student could vote and then I would stop. Or 40% chance the first person doesn't vote and I have to ask a second student and maybe they vote. And so that would be 60% chance, right? But then they might not have voted, 40% chance. And then the third student could have voted, right? Which is yes, 60% chance. That's the case where I would stop. No, then yes, because we're finding the probability that we have to ask exactly three students. So the third student is the one that voted. And this could keep going on forever. There's no real end point here. We just stop whenever we get to the first success, right? So this situation where we're talking not about a number out of successes out of a number, but we're talking about trying things one after another until we get to the first success and recording the number of the trial. That's called a geometric model. And it has a different structure, right? In this case, we would have to take 1, 2, so 2.4 fail probabilities, and then finally multiply it by 1 success probability, okay? So we'll always have like some number of no's multiplied by 1 yes probability at the end for the last one. So the structure is a little easier. Sometimes people don't even bother with the model in the calculator. They just do this directly, okay? But there is a model in the function, or the calculator has a function. It's called geomet_PDF for the probability that the first success occurs on a specific trial, or geometric CDF is the probability that the first success is on or before the kth trial. So let's look at some specific examples, right? If I wanted to do this problem over here, the probability of having this happen on the third, so the probability that we would have, so maybe if I were to draw it like this, I could say, all right, let's make a little model. X represents the which student is the first to vote that we encounter, okay? So there's no 0 here because we're definitely going to ask one student. This one starts at 1. Binomial starts at 0 because we're counting and could have 0 successes. Could be the first student or the second student or the third student or the fourth student or the fifth student, and this has no end. We could keep going forever until we find somebody who voted. Okay, so if I'm trying to find the probability that it's we have to ask exactly 3 students. In other words, it's the third student that's the first success. The probability that the third student voted is the first that we find to vote, right? That could be found with a geometric PDF function, P, because it's a particular single value, PDF. Now, what we have to enter for that is a little different. Okay, if we look at it, right at the very bottom. So actually, if you go second variables, if you scroll up, you'll wrap around the bottom. We only have to enter 2 things. We have to enter the probability of voting, which in this case is that, and then the value, right? Because there is no end value, so we just enter which number we're interested in, right? So in this case, it would be there's a 60% chance of voting. And we're going to stop when we get to the third student. What's the probability that this third student is where we stop? That's 0.096, okay? Or 0.4 times 0.4 times 0.6. All right, what if we asked it this way? If you keep asking students, what's the probability you have to ask more than 3 students? Okay, so let me make my little kind of picture there. X representing the position of the first voter that we find, right? The first student, the second student, the third, the fourth, the fifth. What's the probability that we have to ask more than 3? So more than 3 is over here, right? This probability and this probability have to add to 1. So to find this probability, I'm going to use geomet CDF, right? The cumulative total. There's a 60% chance of voting up to 3. That would be the same as adding a geometric PDF for 1, 2, and 3 together. But there is a geometric CDF right at the very bottom, right? Probability of voting 60% up to and including the third. That means there is a 96.3% chance of finding a voter within the first 3 students, and therefore there's a 1 minus that probability. So this probability over here that we're after is 1 minus 0.936, which would be 0.064. So there's only a 6.4% chance that we have to ask more than 3 students before we find a voter. All right. So binomial is about finding the probability of a count out of a total. Geometric is about the probability that the first success occurs at a specific position in the trials in order. All right. Okay, with that, we can go ahead and have you try problem number 8, which is the second problem in your required practice packet. So give that a try. Pause the video, unpause when you're done, and I'll go over it, and then we'll wrap this video up. Okay, this says, suppose that a computer chip manufacturer rejects 2% of the chips because they fail the testing. What's the probability that the 5th chip you test is the first bad one that you find? Okay, so I would make my little drawing here. X is going to be the position of the first failed chip. The probability of yes, in this case, I'm calling finding a failure, and that's going to be 2%, so 0.02. All right? So it could fail on the first chip, second chip, third chip, fourth chip, fifth chip, sixth chip, seventh chip, eighth chip, keep going forever, right? What's the probability that exactly the 5th chip is the first one to fail? So that one is going to be geometric PDF, right? And let's see, the probability of failure here is 2%, and we want that it fails on the 5th one. So that would be second variables, geometric PDF, probability of failure 0.02, failing on the 5th one. It's going to happen with only a 0.0184% probability, less than 2% chance of that happening. Okay, the second problem there says, what's the probability that you find a bad one within the first 10? So here we've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, it keeps going, right? Within the first 10 means you find the first one somewhere in the first 10, okay? So that can be done with the geometric CDF function, cumulative, chance of a failure 2% up to and including the 10th chip. So if I go to second vars, very at one at the bottom, right, there's a 2% chance of an individual chip failing. That it fails up to 10th trial well, there's an 18.29% chance of finding a failing chip within the first 10. All right. Okay. All right, so just to wrap this up, there's one last thing, and that is I just want to compare these 3 scenarios real quick to talk about this Bernoulli trial thing. Let's say that we drew 2 cards from a deck of cards, and we wanted to find the probability that they are kings, that both of them are kings, right? So the first one would have to be a king, and the second one would have to be a king, right? Well, the probability that we have a king is there's let's see, a king for each of the 4 suits. So there's 4 kings in the deck out of 52 cards. But remember, when we have and probability, this and this, we have to multiply, and the second has to be conditional. So we have to say, what's the probability of the second one being a king, given that the first one was a king? So if that's true, that king is out of the deck. So there's only 3 of them left out of the remaining 51 cards. And that means the probability of finding a king is not staying constant, right? So this one here, this is not a Bernoulli trial, right? One of the requirements for a Bernoulli trial is, like in those voter scenarios, the probability of every individual student voting was always 60%, regardless of where in the tree and where you were in the trial list. Here, the probability is changing from trial to trial, so we could not use anything like a binomial or a geometric model here. Could not use binomial. Could you use binomial or geometric? No, we can't use it here because this doesn't have a constant probability. Okay, if you flip a fair coin twice, what's the probability that you get tails both times? Well, the probability that the first one's tails, if it's a fair coin, is 50%. The probability of the second one is 50%, right? So this is a Bernoulli trial. Multiple trials, same thing. Yep, we could use Bernoulli or geometric to solve problems like this, right? What about this one? If a ball pit in a McDonald's play area contains 10,000 balls and 10% of them are green, what's the probability that if you chose 2 balls, they would both be green? Okay, well, the probability that the first one would be green would be 10% of the balls are green. So that means there'd be 1,000 green balls out of the 10,000 balls, right? And then we'd multiply by the second one, which would mean one of the green balls is gone. So it's 999 out of 9,999, right? But this probability is 10%. And this probability, 999 out of 9999, is 0.0990999, which is very close to 0.1, right? In fact, it's so close that this is approximately the same probability, right? So there's a rule of thumb. We're going to say yes, even though the probability is not staying constant. And here's the rule. If you're sampling less than 10% of the population, you can assume that the probability of whatever you're looking at is approximately constant, right? And so we could use a Bernoulli or a geometric model in this case, because with 2 balls, we're sampling less than 10% of the balls. So this probability, although it's slightly changing, it's so close to being the same that it's basically the same. And so we can use that. All right. All right, that's going to wrap this up. We'll have a part 2 video, which will cover a couple of odds and ends, but we've already covered the majority of chapter 17 here.